You have probably experienced it before. You think of someone you have not seen in years, and the next day they call you. Or perhaps you learned a new word, only to suddenly encounter it 3 times in the same week. Maybe you noticed that buses tend to arrive in clusters rather than at evenly spaced intervals. These seemingly impossible coincidences might feel like the universe is playing tricks on you, but what if there was a scientific explanation, a strange law of nature that actually predicts these occurrences? In 1922, a mathematician named William Feller published a groundbreaking paper on probability theory. His work contained a pattern that would later become recognized as one of the most counterintuitive yet mathematically sound principles in statistics. However, it was not until 1979 that mathematician Percy Diaconis and statistician Frederick Mosteller coined the term the law of truly large numbers to describe this phenomenon. Their definition was simple yet profound. With a large enough sample, any outrageous thing is likely to happen. This principle works alongside what we now call Littlewood's law, named after Cambridge mathematician J. E. Littlewood, who proposed in the 1980s that an individual experiences what seems like a miracle roughly once per month. His calculation was straightforward. Assuming a person is awake for 8 hours a day, they experience 1 event per second, resulting in about 1 million events per month. If we define a miracle as a 1 in a million event, statistically speaking, each person should experience approximately 1 miracle every month. Dr. Olivia Yang, a computational neuroscientist at Stanford University, has spent the last decade studying how our brains process coincidences. What fascinates me is not just that coincidences occur with mathematical regularity, but that our brains are specifically wired to notice them, she explains. We evolved to detect patterns as a survival mechanism, which makes us exceptionally good at spotting connections but terrible at understanding randomness. This evolutionary quirk creates what scientists call an apophenia bias, our tendency to perceive meaningful patterns in random data. In a 2018 study published in the Journal of Cognitive Neuroscience, Dr. Yang and her team used functional MRI to observe brain activity when subjects were presented with coincidental versus non-coincidental information. The results showed heightened activity in the anterior cingulate cortex, an area associated with conflict monitoring and attention, when participants encountered coincidences. What we are dealing with is actually a collection of related mathematical principles that together explain why coincidences are not just common but inevitable. The first is the birthday paradox, which demonstrates how our intuition about probability often fails us. In a room of just 23 people, the probability that 2 share a birthday exceeds 50%. With 70 people, this probability rises to 99.9%. This counterintuitive result stems from the fact that we need to consider not just the probability of one specific person sharing your birthday, but the probability of any 2 people sharing a birthday, a much larger number of possible combinations. The mathematics behind coincidences is fascinating because it reveals how poorly calibrated our intuition is when it comes to large numbers and combinations, says Dr. Evan Lewis, a mathematician at MIT who specializes in probability theory. Our brains evolved in environments where we rarely had to consider millions or billions of possibilities simultaneously. Another component of this weird law is the clustering illusion, formally described by psychologist Thomas Gilovich in 1985. This principle explains why random processes often appear to create patterns. Take the classic example of coin flips. If you flip a fair coin enough times, you will inevitably encounter sequences that seem non-random, such as 10 heads in a row. This happens not because the coin is biased, but because long sequences are a mathematical certainty given enough trials. This relates directly to what statisticians call the law of large numbers, formulated by Jacob Bernoulli in the early 18th century. The principle states that as a sample size grows, the average of the results gets closer to the expected value. However, its counterpart, the law of truly large numbers, explains why extremely rare events must occur when the sample size is enormous. Consider the lottery. The odds of winning a major jackpot are approximately 1 in 300 million for some games. These odds are so remote that for an individual, winning seems impossible. Yet someone almost always eventually wins. Why? Because millions of people play. The law of truly large numbers dictates that with enough participants, even the most improbable outcome becomes a near certainty for someone. This brings us to the Baader-Meinhof phenomenon, or frequency illusion, officially documented by linguist Arnold Zwicky in 2006. This occurs when you learn about something new, then suddenly notice it everywhere. You learn a new word, and suddenly everyone seems to be using it. You buy a new car model, and suddenly see the same model all over the roads. The phenomenon actually combines two cognitive processes, selective attention and confirmation bias. Selective attention causes your brain to notice the new information that was previously filtered out as irrelevant background, while confirmation bias reinforces the perceived frequency. What is particularly interesting about the frequency illusion is that it reveals how much information our brains typically filter out, says Dr. Yang. We are constantly bombarded with stimuli, and our attention systems must be highly selective. Once something becomes relevant to us, our perceptual system flags similar stimuli that were always there but previously ignored. Perhaps the most striking real-world manifestation of these principles is Benford's law, discovered by physicist Frank Benford in 1938. This law predicts the distribution of first digits in many naturally occurring collections of numbers. Contrary to what intuition might suggest, in many datasets, the number 1 appears as the first digit about 30% of the time, while 9 appears only about 5% of the time. This logarithmic distribution applies to an astonishing range of datasets: river lengths, population figures, stock prices, physical constants, and even numbers in newspaper articles. The pattern is so reliable that forensic accountants use Benford's law to detect financial fraud by identifying datasets that do not follow this natural distribution. A particularly fascinating application of these principles occurs in what statisticians call the waiting time paradox or inspection paradox. Imagine you arrive randomly at a bus stop. Your intuition might suggest that, on average, you would wait half the time between scheduled bus arrivals. But in reality, you will likely wait longer. This is because you are more likely to arrive during a longer than average gap between buses simply because longer gaps provide more opportunities for your random arrival. This explains why people often feel buses come in clusters, explains Dr. Lewis. It is not just perception. Random arrivals at service points genuinely experience longer average wait times than would be calculated from the schedule alone. Then there is Parando's paradox, discovered by Spanish physicist Juan Parando in the late 1990s. This mathematical curiosity demonstrates how two losing strategies, when alternated in the right pattern, can become a winning strategy. The principle has profound implications for understanding everything from gambling systems to biological evolution, climate patterns, and investment strategies. Parando's paradox shows us that in complex systems, the combination of failing parts can sometimes produce success, says Dr. Lewis. This helps explain why evolution can progress through seemingly disadvantageous intermediate stages, or why certain economic policies might work despite appearing counterproductive in isolation. The science of coincidence extends even further into the realm of network theory, where the small world phenomenon explains why we are all seemingly connected by 6 degrees of separation. This concept, first proposed by social psychologist Stanley Milgram in 1967 and mathematically formalized by Duncan Watts and Stephen Strogatz in 1998, demonstrates that even in vast networks, short paths typically exist between any two nodes. This network property helps explain why you might unexpectedly discover that your new colleague once dated your cousin's roommate. It is not magic, it is mathematics. In a world of nearly 8 billion people, the number of potential connections between individuals creates trillions of possible paths, making such discoveries statistically inevitable. What makes coincidences feel special is not their occurrence but their relevance, says Dr. Yang. We notice when we think about a friend just before they call, but we do not keep track of the thousands of times we think of someone and do not hear from them. In 2006, mathematician Joseph Mazur published a book titled "What's Luck Got to Do with It?", where he calculated the odds of various coincidences. For instance, the probability of thinking about someone for the first time in years and then receiving their call within 24 hours is about 1 in 10,000, unlikely, but given that such opportunities arise multiple times in our lives, most people will experience this at least once. A mathematical model that ties many of these principles together is the Poisson distribution, developed by French mathematician Simeon Denis Poisson in 1838. This distribution describes the probability of a given number of events occurring within a fixed interval of time or space, assuming these events happen at a constant average rate independently of the time since the last event. The Poisson distribution explains why rare events often appear to come in clusters. If shark attacks follow a Poisson distribution, which they approximately do, then periods with multiple attacks in quick succession are mathematically expected, not anomalous. The same applies to airplane crashes, lottery winners from the same town, or lightning strikes in the same area. The Poisson clumping heuristic, as it is known in statistics, demonstrates why clusters of rare events are not just possible but inevitable, explains Dr. Lewis. What seems like an extraordinary coincidence is actually a mathematical certainty given enough time and opportunities. Perhaps most remarkable is how these mathematical principles extend across disciplines. In ecology, Robert May's work in the 1970s showed how seemingly random fluctuations in population dynamics follow predictable mathematical patterns. In quantum physics, the seemingly random behavior of particles is governed by probability distributions that predict, with astonishing accuracy, the likelihood of various outcomes. Even in geology, the distribution of earthquakes follows power laws that explain why certain patterns emerge. The Gutenberg-Richter law, developed in the 1950s, describes the relationship between earthquake magnitude and frequency, showing that while large earthquakes are rare, their occurrence is not coincidental but follows strict mathematical rules. These intersecting principles create what statistician David Hand termed in 2014 as the improbability principle, which states that extremely improbable events are commonplace. The principle combines the law of truly large numbers, the law of selection, the law of the probability lever, the law of near enough, and the law of inevitability to explain why coincidences are not just possible but guaranteed. What most people fail to grasp is the sheer scale of opportunities for coincidence in modern life, says Dr. Yang. In a world with billions of people having thousands of experiences daily, connecting through social media and global communications, the number of potential coincidences is astronomical. Consider a simple calculation: if each of the world's 8 billion people has just 10 significant experiences per day, that creates 80 billion daily events. The number of potential pairings between these events is approximately 3.2 quintillion. With this many possibilities, even events with 1 in a billion odds would occur thousands of times daily worldwide. This mathematics of coincidence helps explain phenomena like multiple scientists independently making the same discovery at nearly the same time, what historians of science call multiple discovery. Famous examples include the simultaneous development of calculus by Newton and Leibniz in the 17th century, the independent formulation of the theory of evolution by Darwin and Wallace in the 19th century, and the parallel discovery of the expanding universe by Lemaitre and Hubble in the early 20th century. When the necessary intellectual building blocks are in place and a problem becomes solvable, it is almost inevitable that multiple researchers will arrive at similar solutions, explains Dr. Lewis. What appears to be an extraordinary coincidence is actually the predictable outcome of scientific progress. Even in our personal lives, the mathematics of coincidence governs experiences we find remarkable. Consider the case of Laura Buxton, a 10-year-old girl from Staffordshire, England, who in 2001 released a balloon with her name and address. The balloon was found by another 10-year-old girl also named Laura Buxton, living 140 miles away. This coincidence received media attention as seemingly miraculous. However, statisticians point out several factors that make this less improbable than it appears. There were thousands of balloons released in similar experiments, though we only hear about the coincidental ones. Laura was a common name for girls born in that era, and the finders specifically sought out another Laura Buxton after reading the balloon tag. When examined through the lens of selection bias and the law of truly large numbers, such coincidences become expected occurrences. The key insight is not that coincidences are impossible, but that they are inevitable, says Dr. Yang. What deserves our awe is not that coincidences occur, but that mathematical principles can predict their occurrence with remarkable accuracy. These principles even extend to understanding why certain conspiracy theories persist despite contrary evidence. The clustering illusion and apophenia bias explain why people might see patterns in stock market fluctuations, political events, or global health incidents that are actually the result of random processes or independent factors. In a 2012 study published in Psychological Science, researchers demonstrated that inducing a sense of lack of control in participants increased their tendency to perceive patterns in random data and to endorse conspiracy theories. Our discomfort with randomness drives us to find patterns, even when none exist. Understanding the mathematics of coincidence is not just an intellectual curiosity, it has practical applications, explains Dr. Lewis. It helps us design better clinical trials, create more effective public policies, develop more accurate financial models, and even improve artificial intelligence systems. Indeed, machine learning algorithms must be carefully designed to avoid being fooled by the same statistical mirages that catch human attention. The phenomenon known as overfitting occurs when an algorithm mistakes random noise for meaningful patterns, essentially, the algorithmic equivalent of seeing faces in clouds or conspiracies in coincidences. The science of coincidence also helps explain the hot hand fallacy in sports, where observers believe a player who has made several successful shots is more likely to make the next one. Studies dating back to Gilovich, Vallone, and Tversky's groundbreaking 1985 paper have shown that in most cases, the hot hand is simply a misperception of random sequences. However, recent research has revealed that in some contexts, success may indeed marginally increase the probability of subsequent success due to psychological factors. The interplay between genuine patterns and our perception of them is fascinating, says Dr. Yang. Sometimes what looks like randomness contains hidden order, and sometimes apparent patterns are completely illusory. Perhaps most profound is how these principles help us understand our place in the universe. The anthropic principle in cosmology, formulated in the 1970s, addresses why the fundamental constants of nature seem fine-tuned to allow for life. While this might seem like an extraordinary coincidence suggesting intelligent design, the principle offers an alternative explanation. In a multiverse with varying physical laws, we necessarily find ourselves in one of the universes compatible with our existence. When we appreciate the full scope of these mathematical principles, we gain a different perspective on reality, reflects Dr. Lewis. What seems magical or mysterious often turns out to be the inevitable consequence of probability at scale. So the next time you experience a remarkable coincidence, running into an old friend in a foreign country, thinking of a song moments before it plays on the radio, or dreaming about an event that later occurs, remember that you are not witnessing the suspension of natural law. Rather, you are observing the perfect functioning of the weird law of nature that predicts coincidences, the mathematical certainty that in a world of countless interactions and limitless opportunities, the improbable becomes inevitable. The true wonder lies not in the coincidences themselves, but in our ability to understand them, to see beyond the apparent magic to the elegant mathematics beneath. In a universe governed by probability and statistics, coincidences are not exceptions to the rules. They are the rules, written in the language of numbers, playing out across the vast canvas of existence.